Have you ever stopped to think about what it really means to compute something? I mean, before we had laptops, before we even had calculators, what was the most basic, bare bones idea of a calculation? Well, let's dig into that, because the answer comes from this brilliant, totally imaginary machine that, get this, became the blueprint for every computer you've ever used. So to really get why this invention was such a game changer, we have to go back in time. Back to an era before computers existed, when some of the world's greatest minds were stuck on a huge philosophical problem. I mean, really think about that for a second. If you don't have a computer to just run the code, how could you possibly prove that a certain method for solving a problem would always work for any possible input? This wasn't just a practical puzzle. It was a really deep question about the fundamental limits of logic itself. And this question had a name. It was called the Entscheidungsproblem, or the decision problem, and it was posed by the famous mathematician David Hilbert. He basically threw down this challenge to the entire world. Find me a universal algorithm, a step-by-step method that can take any mathematical statement you can think of and tell me, yes or no, is this provable? He was literally looking for a single recipe to solve all of math. The only problem? Nobody could find it. And this is where a young Alan Turing walks onto the stage in 1936. Instead of trying to find this mythical universal method, he completely flipped the problem on its head. He realized that to prove whether such a method existed, you first had to define what a method even is. And he did it with a thought experiment. Now, this is the most important part to get right off the bat. The Turing machine was not a real physical thing. You couldn't build it with gears and wires. It was an idea, a concept, an abstract machine designed to be as simple as humanly possible, but powerful enough to perform any calculation you could dream of. Okay, so it only has 3 parts. Part 1, an infinite tape. Just imagine an old film reel that goes on forever in both directions. It's split into little squares, and each square can hold just one symbol, like a 1 or a 0. This tape is the machine's entire memory. That's it. Part 2, a read/write head. This is the part that does all the work. It just hovers over one square at a time, and it can do 3 really simple things. It can read the symbol on the square, it can erase that symbol and write a new one, and it can move one square to the left or one square to the right. It's kind of like the machine's laser focus, its processor. And finally, part 3, a simple set of rules. This is the machine's program, but it's not software like we think of today. It's just a tiny instruction book that tells the head exactly what to do based on what symbol it's currently looking at. And that is the whole shebang. An infinite tape, a simple head, and a little rulebook. It seems almost ridiculously basic, right? But with just these 3 things, Turing was about to change the world. So that's a lot of theory. It all sounds pretty abstract. So let's make it real. Let's actually watch a Turing machine do its thing and perform a super simple calculation. We're going to give it a very basic job. We're going to represent numbers just by using a series of 1s. So the number 2 would just be 1, 1 on the tape. Our goal is to get the machine to take 1, 1 and turn it into 1, 1, 1. In other words, we're asking it to add 1. Now, the program to do this is incredibly simple. It's literally just 2 rules. The first rule is for moving. It says, if you're in the starting state and you see a 1, just move 1 square to the left and switch to the next state. The second rule is for writing. If you're in that next state and you find a blank square, which we'll call a 0, just write a 1 in its place and then stop. That's the entire program. Okay, let's run it. The machine starts up in its initial state, Q0, and the head is sitting on the rightmost one of our number, 11. It checks its rule book. Rule 1 says, see a 1, move left. So it does. It just scoots over 1 square. Simple. So now the machine is in its new state, Q1, and the head is hovering over a blank square. It checks its rules again. Rule 2 says, see a blank, write a 1. So it erases the blank and writes a 1. Then that same rule tells it to go to the final state, which means halt, stop. And that's it. The process is over. The machine stops. We started with 2 1s on the tape, and now, look, we have 3 1s. It worked. It successfully added 1. Okay, so the machine did a basic piece of math. Big deal, right? Well, what we just watched was way more than just simple arithmetic. It was a perfect demonstration that a totally rigid, mechanical set of rules can produce a guaranteed correct result. And that idea, it has some absolutely profound implications. So why does any of this matter? How in the world do we get from adding a 1 on some imaginary tape to the supercomputer that you carry around in your pocket every single day? And here it is. This is the mind-blowing part. Turing proved that his simple, imaginary machine is basically the theoretical ceiling for computation. Your laptop, a government supercomputer, even some futuristic quantum computer, they might be millions of times faster, sure, but they can't solve any problem that this simple machine couldn't, in principle, also solve. It defines the absolute outer boundary of what is computable. And you can see its DNA everywhere today. The Turing machine's whole approach, changing things step by step, one instruction at a time, is the direct ancestor of what we call imperative programming. Think of languages like C++ or Java. But what's really fascinating is that a totally different way of thinking about computation, called lambda calculus, popped up around the same time. It's based on pure functions. Well, it turns out it's just as powerful, and it became the foundation for functional programming, languages like Haskell. It's amazing. The same core idea of computation led to two completely different, massive families of modern software. So let's just take a step back and appreciate the incredible, lasting legacy of this thought experiment from all the way back in 1936. It really all boils down to this. Turing didn't just invent a machine. He gave us a formal definition of what computation is. He created a conceptual tool that could, in theory, calculate anything that is possible to calculate. So by defining what a machine could do, Turing also managed to prove what it couldn't. He answered Hilbert's big decision problem with a no. That universal algorithm he was looking for just isn't possible. And in doing all that, he gave us the theoretical blueprint for the entire digital age. He showed us how a few simple rules can create breathtaking complexity, and he basically laid the foundation for the entire field we now call computer science. Every single computer we have ever built, everything we call computation, lives inside the boundaries that Alan Turing sketched out nearly a century ago. This simple machine represents a universal limit, which leaves us with one last, pretty deep question. Is there anything beyond that limit? And if there is, what would a machine that could go there even look like?